lower the bandwidth.
Okay, so that's going to be the last technical talk. After that, we'll be having the concluding and the initiating talk. So the talk with which you can start and you can finish this series of expositions. So today we talk about this convergence in scaling limit theorems, and two talks ago we discussed the case of one point, of single point perturbation of the maximal stable state, which is all three. And now I will explain what happens if you add more points. And I think today is going to be a little bit longer and a little bit more technical, but I'll try my best to explain how this goes. Okay.
Nevertheless, by the abelian property, it is the same final state, if not the dynamics, to perturb one by one of the points than all of the finite number of points, or not?
So it's not exactly the same because, well, this was our strategy a long time ago to understand this thing. So at one point, see what happens, and then at next point. But then you enter into very complicated domain of interacting for the solitons and the boundary. So, for example, you have some piece of the boundary, and then a soliton enters. You need to analyze those things like does the wave pass from one side to another? Sometimes it does, and it complicates the story greatly. So we found alternative way to approach this, which works, and I'll explain today in some details.
Very good.
Okay, so first I recall that last time we talked about the purely tropical model, which is inspired by the sandpile model, which is called tropical sandpile, and there you deal with admissible domains, or let's say on the plane, and for a single point in the interior we defined the operator GP, which plays a crucial role in all this business, which acts on the set of omega tropical series and morally, it's like adding a grain at P, relaxing and removing the grain. And the important thing is that for different points, those operators do not commute. So you apply one, then the other, and it's not the same as in the other way around. Yeah. So for a finite subset of the interior, we considered the relaxation, which is a process of applying these operators with lower index from this finite set. And what was the main result? One of the main results was that this process always converges to some omega tropical series Fp omega, and this is the result of the relaxation. And there are a few things to tell about this. These things. So first of all, we know that GP is an idempotent operator. So imagine you are already did this relaxation after adding point and then remove the point. Then if you add the point, there is no need to relax. You remove the point, nothing happened. So that's why morally this GP is idempotent. And so if you have a single perturbation point, then your relaxation at the tropical level consists of a single step. You start with the zero tropical series, which is like all three state, and you pass to GP of O omega, and that's it. If you have 2 points, then you essentially have only two relaxation sequences. One starts with GP and other starts with GQ, but in general term will be something like GP GQ to the power of m and probably GP after that. So that's for 2 points, there are only two relaxation sequences. If there are more points, there are many more ways to proceed during this relaxation, and the result, nevertheless, will be always the same. Okay. So this uniform limit of the relaxation, this series FP omega, it doesn't depend on the order of gradient operators in this relaxation and is characterized by the property that it's the pointwise minimum of all omega tropical series that are not linear at these points where you perturb your state.
Here I'm a little bit confused because here there seem to be two realms or the scaling limit in between. I forgot a little bit the notation, but GP was an operator on sandpiles, a discrete.
No, it wasn't.
It's already the operator on the linear.
Yes.
In the piecewise linear functions. Okay, it's the one that changed the coefficient by 1. And
yeah, exactly.
Right? Okay.
It changes the single coefficient so that the defined curve passes through the perturbation point. Okay.
What is still true though is that this change uses the integral affine structure, right? This is still true. So while it's mostly a continuous object, there is this kind of continuous piece or discrete piece. Integral affine structure.
It's a piecewise linear object.
It's a piecewise linear object, but the GP operator changes by these discrete pieces, isn't it?
No, not at all. So I remind you, you simply increase one coefficient of the tropical series, and yeah, you can imagine it as a continuous process. So you increase it continuously, not by one, but by infinitesimal. And at some moment, a phase of your tropical curve passes the boundary of it passes through the point P, and then you add. And so let me.
Yeah. You can define then this interpolation of change in GP, but GP itself just one action. At some point, you have to choose a scale for GP.
No. You're confusing two things. So one is the continuous change, and other one is the result of this continuous change, the terminal position of this change.
Okay.
So
just remind me very quickly. Just remind me very quickly GP.
So yes, I'll do it right now. Right now, I remind you how it goes. So imagine you have the face. And the point is somewhere here.
That's right, yeah.
Then what you are imagining, you're imagining a process of shrinking this face. But GP is just the result of this shrinking.
That's right. This is, yeah, maybe I was saying it wrong, but what I meant to say is that because these are rational slopes, and because P must have integral coordinates, I believe, is that so?
Yes.
So the integral affine structure is still very important in the definition of GP.
Yes, of course.
And there is still some discreteness to GP in that it only lands at these integral points. Of course, this is not important for the definition of GP itself. P could have any coordinates. But for the validity of the whole theorems and the processes that we're imagining, this combinatorial discreteness, let me call it, it's important so that the processes will really behave the way
Yes. That's right.
Yeah, that was all my remark.
Okay, good. Let's continue then. So this was about the relaxations, and the result of this relaxation, FP omega, I just told a couple of minutes ago that it can be characterized uniquely as some omega tropical series, which is minimal in terms of the action, if you like, among those which are not linear at P. And we learned about this FP omega studying sandpiles. And this arises in the scaling limit theorems. So 2 talks ago, I spent 3 slides on stating these theorems, and now I spent just 1 slide. So I spell all of them at once. So we are still in this tropical sandpile setup. So we have omega, we have this subset of the interior of omega, which is P. And now one more piece of input is H greater than 0, which is the scale of the lattice. And we have omega with lower index H, which is omega interior with intersection with the lattice of this size. And there is something mysterious for the moment, and I'll explain later what it is. We have to introduce the notion of properness for roundings. Last time roundings was something for a point P, which is nearby and in the lattice. Now it's more subtle. For now, let's forget about it. Subtlety, let's imagine that is just any roundings. And so we are looking at the perturbation of the all 3 state. So this one. All 3 state at these roundings of the perturbation points P. And there are 3 versions of the scaling limit theorem. Like the first version, most visual, it's just about where the result of the relaxation is less than 3. And we call this set deviation locus, and it converges to the curve defined by this tropical series FP omega. Then this first scaling limit theorem only restores the set, the underlying set of the tropical curve. It doesn't know the multiplicities, and so that's why it's interesting to consider the quantitative deviation, this h minus 1, 3 minus phi h0, which measures how far you are from all 3. And this weak star converges to some distribution on this tropical curve. And from this distribution, you restore the multiplicities on edges. And finally, the most elegant version is about the pointwise convergence of the toppling functions, rescaled by h. And they simply converge to FP omega. Okay? So
just a question about the logic, because something is I forgot something. Is C strictly implies B, or it doesn't strictly imply B? C.
Almost. So we don't deduce C from B, from A, or whatever. We are rather proving first C, and then we use elements of this proof to prove A and B. And today I will not be speaking at all about B. I speak quite a lot about C, and I'll also finish the proof of A. Because I've shown you a little bit how you deduce one part of this Hausdorff convergence. Remember that Hausdorff convergence is essentially about being in the neighborhood of the deviation locus for this tropical curve. So one is a neighborhood of the other. The sequence is close to its limit, and the limit is close to its sequence.
Yeah.
Okay.
Yeah.
Okay. So now that's this ugly point that I really need to clarify. It's about proper roundings. So I tell it what it is. So first we define the auxiliary function f big, which is the discretization of FP omega. So it's defined as the integer part of h minus 1 fp omega, yeah, of z. And now the set of roundings is called proper if the Laplacian of this function f is less than 0 at this point. Okay? So, and
well,
why?
it is a definition, but it is mystifying. Why would you choose that condition?
So, so just a second. Could you repeat the question?
No. I just said that it is a definition, but I guess you will explain why you would choose such a peculiar condition.
I explain it just below. I explain it because this is the only way how you can achieve the upper bound. Because
okay.
Because what you want this big F to be the actual upper bound for the toppling function, and remember that phi h was all three plus the delta function at the points P. And so having something strictly less than 0 guarantees that we are relaxing that, yeah, sorry for that. Now it's over. So recall that phi h is all three with some extra grains. And so we want to relax it. And when we add the Laplacian of this f, we should decrease somehow these 4 values. And this is exactly how it's guaranteed. These proper roundings are exactly where this Laplacian is supposed to be strictly less than 0. Okay, so
but I have a little question here. These groundings is what we need, but it's easy to ascertain that they exist, I suppose.
yes, that's one thing I forgot to mention. You prove that they exist. In any situation, they exist, and then I include this slide to soothe you, in a sense that this is a minor technicality to make the theorem general enough. Actually, there are quite satisfactory setups where you avoid these proper roundings whatsoever. So, for example, when you have one perturbation point, we avoided it completely. So I explained how you do with any rounding. Then in somewhat purely combinatorial setup or computer science setup, when you do experiments with computer, when your domain is a lattice polygon and your points are lattice points and your scaling is the inverse integer, then you can take these roundings just tautologically. The point itself, because every point would still belong to the rescaled lattice. And finally, in the geometric setup, when your points are genuinely random, if they are generic, then you also don't need roundings. Any proper roundings would work. Any roundings would be proper in a sense. Well, it's not exactly true what I told you, but it's any roundings would give you the scaling limit. Okay. So now we have upper bound, and now I explain how to derive lower bound. And we are proving the theorem C about the pointwise convergence. So this rounding would be of the form fp omega minus epsilon for this h times h phi h. And this will be achieved by performing a partial relaxation. So we will be doing some topplings and only admissible topplings. Actually, we will be doing only waves. And we will really carve our way through this relaxation in the domain which we understand. So we will be working only with waves applied to solitons. That's the general idea. So everything that follows about this strategy is to assure that our waves, for example, never touch the boundary. Our state never degenerates to something which cannot be described by solitons and triads and those node deformations. So that our curve always stays at most nodal. And and we assure that we do almost all top lengths. So we will we are really able to almost do the whole relaxation process, staying within the domain that we understand. Okay, and now more details about that.
And just to follow this argument, we do almost quality is true, and the other droppings don't destroy it, of course.
Mm-hmm.
Is that the case?
Yeah, I'm not hearing you really well. So could you?
Oh, sorry about that. I said, so just to understand the shape of the argument, we carefully travel through the space of the evolution, this space that we understand. We haven't done all topplings, but almost all of them. And we know that inequality holds after we do this, but we also know that the remaining missing topplings don't destroy the inequality. And that's why.
So we don't know what, formally speaking, we don't know what happens for the last epsilon number of topplings. So
they could destroy the inequality.
No. That's the thing. So the upper bound is just fp omega. The lower bound is fp omega minus epsilon.
That's right.
The upper bound we already have. No, it cannot be destroyed. It's something we start with. But what would be a subject of extra care is to show that the overall configuration after we do the remaining toppling stays essentially the same. And that's the final part of the proof for the theorem A about the Hausdorff limit. So we really need to prove that the last few topplings leave the picture essentially the same.
I see. So it's more elaborate than I thought. Okay.
Yeah. Okay. So now I'll tell you, I'll list the principles of this partial relaxation. And so, first of all, we approximate the domain by, in a very careful, controlled way, by some Q polygon, so polygon with rational sides, and actually unimodular polygon, to be more precise. And there will be some conditions, but essentially this is done to make our situation controllable. So that our tropical series is actually a tropical polynomial, and so that the state we see it can be approximated by the finite tropical objects with having only finite number of edges and so forth. So I'll speak a little bit more about that in the next slide. Then one more thing, we would freeze the topplings outside of this polygon. So this will be one of the remaining topplings, something outside of this approximation. Then other thing, we will start with not with all three states, but actually with some smaller state, which would be made of solitons. And I recall that solitons actually are made of some patterns which are less than 3. So all 3 is the maximal states, and solitons are carved in these all 3 states. And so this will be the reason for some extra topplings when we put back those points. And here we use the abelian property. So we remove some grains and then we put them back, and this causes some extra topplings. Then the relaxation would be performed by sending packs of waves, so one wave after another, from perturbation points. And we will be activating one point at a time. So we send some number of waves from one point, then we send some number of waves from the other, and etc. So we jump from one point to another. And in this process of sending waves, we are careful not to do too much of wave sending, so that at the tropical level, our faces don't collapse. And I recall that if they don't collapse, we stay within this domain of at most nodal curves. And finally, remember I was telling that we don't know yet if this relaxation at the tropical level even terminates. So we know that it uniformly converges, but we don't know if it terminates. So as a technical thing that we do, we actually truncate this tropical relaxation after some good approximation of the limit is achieved. And now I'll speak about each principle in one slide at a time. So any questions so far? So this is the global strategy of deriving the lower bound. Is it too much? But that's pretty much all the important ideas. With that, you can prove it yourself.
Just to understand, we are assuming that we have a rational polygon in this case.
No, we start with any convex domain.
Okay, and so freeze the vertices. A is the most confusing to me, sorry.
So remember...
we approximate via del San polytope omega.
Yeah.
We approximate del San polytope omega, okay.
So this pi big... So maybe this is the handwriting as well. So this is pi with big pi with epsilon at the upper script, meaning that this approximation depends on epsilon, which goes to 0. So in this one point case, our approximation is exactly the thing that you have from this canonical evolution, derived by the canonical class at the space of convex domains. This will be exactly
so I'm allowed to imagine that omega is the circle and that we have this tree.
Yes.
One of polygons.
That's what happens in the one point case when you perturb with one point. When you perturb with more points, then it's slightly different, but still similar in the spirit.
Okay. And in higher dimensions, much more complicated, of course.
Yeah, I don't know if it even works well. So that's the subject of the current study. Okay. Yeah, as I told, we need this approximation for the limiting tropical series to be actually a polynomial. And we choose this pi epsilon so that this tropical polynomial is close to the original tropical series, and that the quasi-degree, I'm not supposing that you remember, but this is something like degree of these tropical polynomials is nice in a very precise technical setting. So this quasi-degree is something like the slope near the boundary. So if it's minimal slope, it's 1. If it's twice the minimal slope, then it's 2, and etc. And so there is some very technical condition we need to satisfy, and which is easy to satisfy, that the quasi-degree of this tropical polynomial is nice, and this would guarantee that actually there exists some tropical polynomial with the same quasi-degree, which is smooth, or whose curve is smooth. And this is what we need for B. Remember, B was that we start with something made of solitons and triads, and yeah, this is where we need this nice assumption. So we construct the auxiliary state as n smoothing of that small polynomial. So this G is something which is almost zero. So it's a big plateau of the constant, and something happens near the boundary. Okay, this will be our initial steps. We kind of construct walls near the boundary of this polygon, and the walls are made of solitons. And important thing that since this G is almost zero, we can start relaxation at the tropical level with this G, and the result will be the same. So, and this auxiliary state is made for the reason that we don't want our waves to touch the boundary. This is kind of delicate. What happens at the corners, where the junction of the corners with solitons, this we virtually don't know. We know the result, but we don't know how to prove it. And this technicality assures that we never need to face it. We just deal with solitons and triads and all the things that we know how to modify when the waves are applied. Okay.
Just to understand again, this G, could you go back a little bit to the G, into 2 slides back?
Yeah.
This G is a new character, isn't it? This had never appeared.
Yes, exactly. So this is some very small tropical polynomial that we use instead of zero as the initial state. And I'll show you how it works for one point. You'll see. So this is this G.
So can I imagine for this? This is an example. Okay.
For the square, the tropical curve would be something near the boundary, so that we can construct solitons following this tropical curve. So this G is almost cut to zero of this pyramid. So on the square, this F omega would be just a pyramid, and G is just the cut almost to zero, so that the edges are following just the boundary of the domain.
Yeah, again, for the circle, I can imagine this pyramid on top of the circle and
you don't do it
cutting
with the circle. For the circle, you don't do it because the first step, you approximate your circle by some polygon. With by possibly a really big number of edges. And then on this polygon, you construct a small tropical polynomial.
That's right. That's right. You have kind of this safe layer close to the boundary.
Exactly.
But my question is, I imagine this pyramid on top of the circle, and of course I cut this pyramid to produce this polygon.
Yeah.
To produce this polygon, and then I further cut the pyramid to produce this layer inside the polygon.
Yes.
So it's kind of these two very thin cuts at the bottom of the pyramid.
Yes, exactly.
Very well.
And so this is this picture is what you would start if you want to do this perturbation at a single point. So this is an important remark. More points you use for the perturbation, more elaborate this initial state G gets. So for just one point, it's what you see. For more points, it should be more complicated. It should be more protected, if you like. The boundary should be surrounded, so should be isolated from the middle by bigger number of solitons. So you need to assure that when you send more waves, more and more waves, your waves never reach the boundary. And for a single point...
I have a little question. So am I allowed to think that this is a further approximation of the boundary by solitons, so to speak?
Yes, exactly.
Very well.
But counted with multiplicities. And this multiplicities is what is called quasi-degree. So it might happen that a certain edge of the boundary is approximated by several edges made of solitons.
Yeah, these kind of parallel lines that you showed in one talk, or?
Yeah, so I can tell you, like, if you have more points, then you would need to double one side. If you have 2 points, you need to assure that the waves that would otherwise reach the boundary would reach the soliton that protects it.
Yeah. I can imagine how it will go, more or less.
So now the principle C is that the relaxation is achieved by doing by sending waves, and here you would send the waves from the middle, and but you should follow also the principle D, which tells you that if your phase is about to collapse, if like in this point, if this wavefront reaches at the tropical level the point of perturbation, then you, at the sandpile level, you actually refrain from doing the last few waves. So you don't want your curve to leave the realm of at most nodal, because this singularity that you see is more severe than just a simple node.
Yeah.
Okay. And now the last principle, I told already, you start with this small g, and you consider the relaxation started from this point. So at some moment, even if this relaxation doesn't stop at the tropical level, we still truncate it. We still, when our result is, let's say, epsilon over 3 close to the limit fp omega, then we stop. We don't do it. Okay, so that was the overview of the strategy for the lower bound, and this is what we achieve. We accomplish more than just the lower bound. We also see that what is done by doing this almost all topplings is actually something near the tropical curve defined by this magnificent series fp omega. Okay, and now
Yeah.
That was something that we did completely in the 1-point case. So since only few topplings remain, and we know where this intermediate state deviates from all three, we know that if we do more of, or we do the last topplings, then it will still sit somewhere near the tropical curve. And that was the lemma that we've proven two times ago, two expositions ago. So, and this wasn't hard, but it leaves us with proving one more thing, that actually every point of the tropical curve is near some deviation locus, so that the deviation locus doesn't have holes. You see what I mean? That every point of the tropical curve is a limiting point, is the accumulation point of the family of the states in the sandpiles. And so that was a place where I found a mistake, like around 3 weeks ago. And a couple of days ago, I finally fixed the mistake, and Nikita tells it's correct. And the argument is really easy. So I'll try to explain it to you. That will be the last thing we do. So this way we will complete the proof of the theorem A. So we will use the following classical theorem, and that we extensively used in our soliton paper. I suggest you contemplate the statement. So, morally, it tells you how to estimate a derivative of a harmonic function on a big domain of harmonicity. So bigger your domain of harmonicity gets, smaller is the derivative in the middle of this domain, of this disk.
So what was the motivation in 1953?
The paper is called discrete potential theory.
Yeah.
So I've never read it, and I've never was able to understand the proof. So this is something like a black box for me. But the result is certainly true, and it's used by many respected people. So this is one of the standard results in this mathematical physics on lattice. Okay.
But the proof is hard.
Yeah, it's not at all Mickey Mouse. It's some hard analysis. Yeah.
Okay.
So now I tell you, we apply this theorem twice to the toppling function of our perturbed state. And so first, let me recall that in this statement, your function is supposed to be non-negative, and our toppling function is always non-negative. And so you have no difficulty to derive this first estimate. So you just apply the theorem, and you lose the dependence on H. But now, what you need to do this thing. You need to add the maximum, and also you need to increase the size of your domain of harmonicity. But then you can apply again this theorem, and you get the following estimate. And here this kappa is an absolute constant, gamma is some moderately big constant, mu is some estimate from the toppling from the tropical series on the compact. And what's important here is H, and I wrote H minus 1 is just H. So
we're already on the second derivative?
Yes, I'm explaining it. So I did the first derivative, and now I do the second derivative.
And why are we all the way to the second derivative?
We are doing the second derivative because we want to prove that it's zero.
Yeah.
We prove it's small, and we remark that it's also an integer. And if it's an integer less than 1, positive, non-negative integer less than 1, then it's 0.
Yeah. And see, here it is what I was mentioning. This integral affine structure is vital here.
Yes, exactly. Otherwise, it's not true. And which implies that your function is actually linear.
Yeah, of course.
If the second derivative is 0. And so now it's very easy. Now imagine you have this H, look below, and you have a hole inside, and you are linear from the two sides, and you are linear in between. And now the contradiction would be is just that the gradient from the both sides of the H should be the same, which is obviously not true, and I'll tell you why, but that's the argument. So if you have a hole in this state, if two big domains of all three are connected through the H, then your toppling function has to be linear on them in the same way, which violates the closeness to this piecewise linear tropical series, which is definitely linear with different gradients from the both sides. Okay, so yeah, so this would violate this twofold estimate. As I told you, this linearity is what you know, that you know the gradient, and you know it exactly for the following reason. So you imagine. So I'm telling you why the gradient of H and of F are the same. So you just consider an interval inside of the face of the tropical curve, let's say horizontal interval. You restrict yourself to this horizontal interval. On the right, you subtract the linear function lambda with the same gradient as F. And if your H has a non-horizontal slope, it has an integer slope, and then you violate very quickly the inequality. Your domain where the inequality can hold is epsilon divided by A. And so it's not big. Eventually, the domain of this linearity. Okay, I hope so. I've rushed a little bit towards the end. I'm not sure about the time, but I hope it was understandable. Do you have any questions?
It was understandable enough. Of course, I would have to go through the details, but it seems very, the argument seems understandable.
Okay. So in this way, we proved that these states at the sandpile level, they have no holes. They really approximate the tropical curve. And this finishes the proof of theorem A. Okay. So shall I stop recording? Or you have some questions?
No, it's perfect.
Okay.